Hi everyone. In this video I plan to annotate the periodic table. This is the main tool that we use and we'll use throughout this whole chemistry unit and throughout year 11 and 12 as well. You'll have it in every test and exam, and so it's really important that we can spot the patterns on the periodic table and use it to do some key skills, to demonstrate some key skills, like writing ionic formulas, predicting ions, talking about reactivity of different elements, etc. All of that comes from some patterns that are built into the periodic table. In this video, I'm assuming that you are already familiar with the way that ions form, what they are, and so I don't need to go over that. I don't need to go over electron configurations and electron shells. I'm assuming that you're comfortable with those topics already. If you're not, please go back and make sure that you are before you come to this. So the periodic table is organized in groups and periods, as we already know, where each column is a group and each row is a period. We can number the periods and the groups in the periodic table. And you'll notice that the groups on the periodic table that I've got printed out here are actually numbered already. But the way that they're numbered is the way that is actually less useful to us for our purposes. So I'm going to go ahead and renumber the groups in this periodic table. So this one here is still group number 1 and this one's still group number 2, but then instead of labeling these groups 3, 4, 5, 6, etc., I'm going to label this whole chunk as the transition elements or metals, and they don't get numbers. These groups don't get numbers. We skip over them and we continue labeling from here. This is group number 3, 4, 5, 6, 7, and 8. And the reason why I've done that is because these numbers now tell us some really important information. The number group that an element belongs to tells me the number of valence electrons that that element has. Let's think about why that's the case. Let's take an element like lithium. Lithium has an atomic number of 3. So lithium is going to have 2 electrons in its first shell and 1 electron in its next shell. As we move over to the next element, beryllium, we're now moving over to group number 2, and we're adding 1 number to its atomic number. So now instead of 3 electrons in total, we're now onto beryllium, and we're going to have 4 electrons in total. We can jump across to boron, where we're now in group number 3, and boron will have 5 electrons in total, and so it will have 3 electrons in its outer shell, 3 valence electrons. And we could continue like that for the whole periodic table and show that every element, the number group that it is in, tells me the number of valence electrons that it has. Why is that so important? It's important because, as you already know, the number of valence electrons that an element has determines the charge that it will have when it forms an ion. So for the metals, lithium, beryllium, let's across to boron as well. These metals will all form cations or positive ions. Let's just spend 1 minute talking about what happens when an element like lithium forms an ion. Let's skip lithium. Let's go down 1 row down to sodium. So sodium has an atomic number of 11, so it's got 2 electrons in its first shell. It's got a full second shell of 8, and then it's got a third shell with 1 valence electron in it. Now, sodium, it's in group number 1, so it has 1 valence electron. And the key here, the key to almost all of chemistry, is understanding that every single element wants to have a full outer shell. That's what every element is striving for. It wants a full outer shell. So for sodium to fill this third shell, it would need to find 7 electrons from somewhere. And that's a pretty big ask. It's pretty hard for it to do. So instead of filling in all the gaps here and getting 7 electrons, it's going to be a lot easier for sodium, in order to get a full outer shell, to actually just get rid of that electron, to give it away to another element. And so it will lose that third shell entirely, and it will now have a full outer shell with 8 electrons in it. And so when sodium forms an ion, because it only had 1 electron in its outer shell, it will form an ion with a charge of +1. And that is true for any element that has 1 valence electron. When it forms an ion, it will lose that electron, and so it will form an ion with a charge of +1. So all of group 1 forms +1 ions. Similarly, all the elements in group 2 form ions with a charge of +2, because they will lose those 2 electrons in order to gain a full outer shell and become stable. Jumping over to group number 3, these elements all have 3 valence electrons, and so they will lose those 3 valence electrons to become stable with a full outer shell and form ions with a charge of +3. I'm going to skip group 4 for a second, because we're going to come back to it a little bit later in the course. But skipping to group 5, we're now past the halfway point. So let's think about nitrogen for a second. Nitrogen has 2 electrons in its first shell, and then it's got 5 electrons in its second shell. For nitrogen to get a full outer shell, it could try and do what the metals did, and get rid of all 5 of its outer electrons. But in this case, because we're past the halfway point now, this shell is more than half full. So it's actually going to be a lot easier for nitrogen to gain 3 extra electrons. And so nitrogen and any other element with 5 valence electrons, when it forms an ion, will gain 3 electrons, and so form a charge of -3. Any element in group number 6 will gain 2 electrons to get a full outer shell, and so it will form a charge of -2. Any element in group number 7 will gain 1 electron. It needs 1 extra valence electron to get a full outer shell of 8, and so it will form ions of charge -1. These elements over on the far right in group number 8, as you know already, are the noble gases. They already have a full outer shell, so we could put a 0 there, continuing the pattern, to say that they don't form charges, they don't form ions, they are content with what they've got a full outer shell already, and they don't need to lose or gain electrons in order to be satisfied. So this is one important pattern of the periodic table. As we go across from group to group, we can easily identify the charge that element will, that an ion of that element will form. Let's think for a second now about reactivity. The key to understanding the pattern of reactivity in the periodic table is understanding the fact that when an element reacts, it is doing so most of the time because it is either losing or gaining electrons. That is when a chemical reaction takes place, when electrons are transferred. Now that's not always the case, but it's an easy way, but it is often the case, and it's going to help us understand another important pattern in the periodic table. So the first thing it's important to understand is that reaction equals electrons. When electrons are moved around, that is where the chemistry happens. The second thing is that if it's easier for electrons to move, then it will necessarily be easier for a reaction to happen. If it's easier for electrons to move, it will be easier for a reaction to happen. And the third thing is that it's important to bear in mind when we're talking about this is that electrons are held in place. What keeps the electron close to orbiting where it is in the first place? Electrons are held in place by the positive charges in an atom, which is, of course, in the nucleus. Are held in place by the nucleus. Electrons are held in place by the nucleus. Let's see why all of that is important. As I mentioned before, the periodic table has groups and it also has periods. Periods are the rows. So we can label these periods period 1, period 2, period 3, period 4, period 5, etc. As we go down to the next period, we are adding an electron shell. So hydrogen has one electron in its one valence electron, and it's only got one electron shell. Lithium also has one valence electron because it's in the same group, but it's now in a second electron shell. Sodium is in group number 3, period number 3, so it's in group number 1, meaning it has one valence electron, but that valence electron is in the third electron shell. Why is that all important? Let's tie all this together, and with this we will finish the video. Let's compare a couple of elements. Let's think about sodium. Sodium has one valence electron, and it is in the third shell. On the other hand, the element 1 down from sodium, potassium, also has one valence electron, but it is in the fourth shell. Now, this valence electron is a lot further away from the nucleus than sodium's valence electron is. That means, since the nucleus is the thing holding the electron in place in the first place, this valence electron will be a lot easier for another atom to steal. That one is easier to steal because it's further away from the nucleus. Therefore, the nucleus doesn't have as strong a grip on it, so it's easier to steal. Whereas this one is harder to steal. Therefore, we can think of that as a pattern in the periodic table, where as we go down a group, we're adding electron shells. And therefore, the valence electron is becoming further and further away from the nucleus. And therefore, as we go down here, and ignore, this is not true for the right-hand side of the table, this is only true for the left-hand side of the table, so make sure you don't get confused. We're going to come back to the right-hand side of the table in a second. But for the metals, as we go down the group, we are getting more reactive because it's becoming easier and easier to steal the electron. Let's finish this video with one last example. Instead of comparing sodium and potassium, let's now compare sodium and magnesium. Sodium has 3 shells and 1 valence electron. Magnesium is also in the third period, so it also has 3 shells, but it is in the second group. So magnesium, instead of 1 valence electron, has 2 valence electrons. Sodium's and magnesium's valence electrons are both roughly the same distance from the nucleus, so that's not going to make a difference. But now, what matters is that sodium only has 1 electron to steal, whereas magnesium has 2, and it's a lot easier to steal 1 than 2. So we can think of it that as we have less valence electrons, it is going to become easier to steal them. So if we add that to our annotation of the periodic table here, just like it's more reactive going down a group because that valence electron is getting further away, and so it's easier to steal. We also get more reactive as we move across in that direction. We're getting more reactive. Now, remember, this is all only true for the left-hand side, for the metals on the periodic table. We haven't spoken about the right-hand side yet. We will in another video. This is my annotation for now. We will add to this soon. Hopefully this all makes sense. Please let me know, either email me or write something in the comments if it doesn't.